begin some physics. That's enough of the preparation stuff. This entire semester is about the physical effects of the existence of electric charge. Most lectures, well, all lectures, will start with a number of the day. It's an interesting number. We'll use this one later in the calculation. This is the conversion from megatons of explosive energy, like in nuclear weapons, to joules. So 1 megaton of explosive energy is 4.184 times 10 to the 15th joules. So we're going to spend all semester talking about electric charge. And electric charge is a feature of every object in the universe. So it's like mass. So it's kind of like a label that's on everything, but it's not actual stuff. So you want to actually find things that are electric charge, but everything will have an electric charge. Now, sometimes an electric charge is zero. So we're going to define electric charge. DFN will be definition. And this will be the first test question. So in effect, we're going to spend all semester defining it. So it's a feature of every object in the universe. And we're going to define it by its effects. For almost all processes, certainly all chemical, all electrical processes, it's the most important feature. All right, and we'll, as we do a calculation at the end of this lecture, we'll be able to compare the strength of the electric force, or the strength of the effect of the electric charge, with the strength of gravity. We'll find it is truly much more stronger. Much stronger. All right, so just a few quick properties. We've got a new thing, so we need a new symbol. We'll either use capital Q or little q for electric charge. We'll use them interchangeably. There's no distinction between them. It's a new thing. We can't make it out of meters, kilograms, or seconds, so we need a unit. The unit is coulomb. And we'll use capital C for coulomb. We're going to start making net charges. So charge is a feature. So a charge should be zero. So the net charge of most of the stuff around you is zero, which is why you don't see the electric force. But we're going to start making net charges in the lab immediately, humidity permitting. And we're going to work hard at it. And we're eventually going to work hard enough that we get sparks out of stuff. Even with that amount of charge, we're not going to produce anything over 10 to the minus 5 coulombs. So that means 1 coulomb is a humongous amount of charge. Charge is additive. Which means if I have two charged things, I put them together, the total charge is just the sum. So the charge of an object is an integer, or is a number, which can be positive or negative. It's not a vector. So charge comes in basically positive, negative, and zero. When we work in lab, we're not counting zero as a third kind of charge. So we'll have positive, negative charge, and no charge or neutral. All right. not going to do much with the atomic properties. Actually, skip the lecture slide. So this is going to be a giant amount of coulombs. So we're going to be dealing with small amounts of charge routinely, so we're going to want some abbreviations to make it easier to write. So we're going to start with millicoulombs. First abbreviation is milli. It's going to be 10 to the minus 3 of something. And so 1 millicoulomb is 10 to the minus 3 coulombs. Millicoulomb is still a lot of charge, so mostly we're going to produce microcoulombs. Be 10 to the minus 6. Micro is mu. 1 microcoulomb is 10 to the minus 6 coulombs. Well, we're producing nanocoulombs. 10 to the minus 9. So 1 nanocoulomb is 10 to the minus 9 coulombs. And we're not going to be able to detect it. We'll more use picofarads. But pico is 10 to the minus 12.